Alrighty, let's see the reminders as usual. Your programming test number 1 is going to be this Thursday during your lab session starting at 9 a.m., right? Like the mock-up test. And I know many of you are going to commute. Please arrange the commute accordingly. It seems like it's going to snow from Wednesday until Thursday. But the official policy will be we'll only cancel the test if the university is shut down, right? So maybe pay attention to weather watch for university. If the university really shut down, then even myself will go, right? So please arrange your commute accordingly, right? Show up in time. And the practice test question has been released, and also solution is also on the e-class. I may not discuss the practice test question themselves in class, but if you got any trouble, let me know. You still have time until, Monday, Tuesday, Wednesday, right, this week to ask me. Office hour and TA contact information, everything's there. But I do want to talk about the Lab2 solution. I'm going to go over the post condition for the suffixes and also right shift problem together with you, just to make sure you can at least understand what's going on. And hopefully you will practice a little bit more to make sure you can also come up with such post condition yourself. That's something I will do. And also, thanks to your fellow students, some of them, they actually gave me some very brilliant solution to the rock, paper, scissors question. I just want to share them with you as well in class, and then you can also learn about some brilliant syntax and concept. I also want to go over that as well. All right. Let's now do some recap very quickly. Before that, any question about anything? Well, for Thursday, the programming test, you know what to do. In order to get prepared, everything has been made available to you. Right? Just let me know if you got any further questions. All right, so last time, we basically just did several exercises. And one kind would be, if you're given some predicate here, of course, I gave you like just a single quantification. But since we already also cover the nested quantification, you can think about if the question was phrased using nested quantification, how are the options that are going to be judged, right? You can think about that too. That's also possible. So we talk about how you can choose the correct options and try to plug in the X and Y to really see why. Some of them may be witnessed and some of them may not be, right? So you can definitely review the detail. So exercise number 1 about universal, exercise number 2 about existential, right? So I think that they're rather straightforward. But of course, this part over here about the predicates and also this part over here about the predicate may be a little bit more complicated in the actual test question. But just got to make sure you learn about the principle first. And then you can just make up some example on your own. And then if you want to check them with me, you're more than welcome to. And then we talk about nested quantification. So I would say you want to pay more attention to not just the specific example that I used last time. You want to pay more attention to if you want to disprove or prove it, for example, for universal at the outer level, how exactly do you apply the proof strategies that we spoke about earlier in the class? That's also somehow the principle I applied last time. Right? So you can really use these 4 examples to start with. Whenever you're given any nested quantification, that's how you can think of. And one of the post conditions I'm going to go over today in the Lab2 solution, it does use nested quantification, right? It's not too bad. You just have to know how to somehow, I'll put in quote, trace it, right? I'm going to show you how you can do it, okay? All right, and then we move on to the model checking lecture. Hopefully we can also do a little bit, make some progress on that today after we go over the Lab2 solution. But I think a Lab2 solution might be more important since you got a lab test coming. Right, so we just talked about some motivating example about in Intel, they actually used the model checking technique after some big loss from their previous recall. So you can feel free to go to this link. It's a very notorious bug for the company. So you can feel free to go there and learn about the historical incident. That really give you some idea about why the model checking has been used in the industry. And then we spoke about 2 notations over here. Both of them are for verification. What you learn in 3342 using the turnstile is really about deriving the property from the axiom, invariance, or guards, whatever stuff you can actually assume in the antecedents, right? So we are trying to do some proving for the verification, right? So that's a proving approach. In general, you just don't really have any automated way to really find out the proof from one to another. So that's why interaction will be so necessary to really, whenever you have a tool to really help you prove. On the other hand, For this one here, which we're going to see once we get to the semantics part for the model temporal logic, it might take us maybe until after the reading week to really get to the precise definition for this. But we want to make sure you're okay with the syntax first. But later on, we're going to see exactly what we mean by a system model, like a label transition system. And then also how the temporal logic formula can be formulated. We'll see some idea from the syntax rule today. All right. So just make sure you understand the difference between this, and also how you compare and contrast them. And then we move on to spoke just a little bit about temporal logic. Well, not temporal logic itself, but really how we're going to discuss it. We're going to talk about syntax first and then the semantics, right? And also that's kind of the typical reaction from the model checker. And TLA plus is what we are focusing on, right? So we'll focus on syntax a little bit more today and Wednesday, and possibly one lecture more, maybe after the reading week. And then we'll get on to defining the meaning for temporal logic. All right, state graph here, we know pretty well. We got a finite number of nodes over here and also finite number of transitions. But given that we have some cycle, that means the number of possible paths you might have from this graph here will be infinite, right? You really want to be sure which one is finite and which one is infinite, right? It's a very crucial distinction to make. All right, that's from last time. Any questions from last time? Any part you want me to clarify? All right, hopefully still straightforward. And what I want to do now is to go over the Lab2 solution and make some highlights, specifically how we understand the post condition. Before I get to task number 3 and task number, I forgot the exact task number, the get suffixes and also shifts. Before I get there, I would like to share 2 solutions with you, not created by me, but by your fellow student. Very brilliant solution. I think the first one here, I just want to show to you how you can generalize the rock, paper, scissors game into, so somehow you want to make the rounds over here, rather than being hard-coded as 2, as you can see from the solution. We can make it either as a constant or variable, and just let the model checker build a graph accordingly. So that means you can set the round to be 2, or can be 3, or can be 4, can be 5, etc. It's a very general approach. I want to show you briefly how you can do it. That's the first one, okay? So just about generalizing the number of rounds. All right, let's take a look. So you can see that this part over here, we got P1R1, and also we got P2R1, right? So here. So this variable here, you can think about, I didn't really change the name that your fellow student put, but you can think about this one here is really about just about what P1 plays. So you can think about this very initial one over here, P1R1 and P1R2, right? So these are the variables, so we are making some non-deterministic choice. We're saying that P1R1 may be any of the members in R, P, or S. And similarly for P2R1, right? Player 1 and player 2. So this will be the initial non-deterministic choice. Initial non-deterministic choices for players in the first round. That's about initialization. And the beauty about this solution here is these 2 variables will be reused, will be somehow updated between the rounds. You can think about, of course, these 2 players are going to play independently. So every time after the current round, let's say after the first round, we're just going to update their choices about what they play, rock, paper, or scissors, right? I'm going to show you that part. It's going to be some very useful syntax you can learn. So you guys can see that this part here is already like a variable here. You can see the rounds over here, and then we also put the rounds right here, right? So the number of iterations is not going to depend on how many rounds we have. It can be 2, can be 5, can be even 10, right? So that's a beauty, okay? And then, so here it's very straightforward. You basically just go to see how they play, right? How they compare and see which one is going to win. That one's very conceivable. I'm pretty sure that's what you did in your solution. That one there, I'm not going to waste your time. I want to focus more on this part over here. This is interesting, right? You can see that this is a while loop. So we got a while loop right here and the end of the while loop. You can see at the end of the iteration, we are trying to do this. Okay, I'm going to highlight it right here. I say with this and with this, and then P1R1 and P2R1. Right? You can see these two variables were already declared P1R1, P2R2. They were initialized right here. And we are just updating the choices at the end of the iteration, just to simulate they're going to play independently again for the next round. Okay? So these two, this one here and this one here. So these are, again, the non-deterministic, like a random. Non-deterministic choices for both players in the next round. Right, depending on how many rounds in total. Let's say if you're currently in the second round, and this update is going to update for the third round, etc. Guys, by the way, I'll also make the maybe the source file because I got your fellow students' permission. I'm also going to share the whole thing with you as well, so you can play with it. Okay, but for now, I just want to discuss certain fragment, so to make sure you can understand. Okay, learn from that. All right, so it's really important for you to see. Let me recap. So you have basically two variables, one for player one, the other one for player two. You have some initial non-deterministic choice. And you make sure at the end of the iteration, you also update the choice. And the way you update them is by use the with syntax. If you somehow go to the, Google a little bit, just see that's the syntax there that's allowed by TLA+. You might find it useful at some point. It's a with, and then with right here. Right? You got some block, and then you got some variable assignments. Right? Also, you got some set to really make the non-deterministic choice from. Right? All right, so after that, outside the loop, we're simply just going to update, the number of rounds won by player one, etc. Of course, the rounds over here can be general, may not be just two. All right, so that's the first solution I would like to share with you. Any question about here? Yeah.
Sorry, how come we don't have like those bits defined for the round two?
We don't have, sorry?
For round two.
For round number two. Right here. So here we say the initial value here was just 2. Of course, you can also feel free to change this one to be 4, and everything here will just work accordingly. Because now the number of iteration for this loop here correspond to the value for rounds. So depending on how large the rounds is.
I don't know. I mean, like when we define two different sets for P1R1 and P2R1.
Okay, I see what you mean. The beauty about this solution here is you don't really have to. Well, a better name or a different name could be, for example, let's say I simply say P1 and P2. Let me get rid of R1, okay? And here I might just say, oh, sorry. Here I might also say maybe here just P1 and P2, not R1. So here P1 and R1 is simply the play they exhibited in the current round you can think about. So you don't need a P1 R1, P1 R2, P1 R3, etc. Just the same variable. They're just going to be kept being updated. Okay. Guys, any question about this? All right, learn about the syntax. I think that's really handy. All right. All right, so the first example here, more about the implementation to make the rock, paper, scissors game more general, independence of how many rounds there are. The second one is also about the rock, paper, scissors. And that one there, I want to share with you about how you can use functions in TLA+ to really, in Pascal, of course, how in Pascal to write some very, very brilliant postcondition. Again, this is really credit to you, a fellow student, not mine. I'm just using their work to kind of share with you the syntax. Okay? So this one here is really using the function syntax in TLA+, and I'll show you exactly what you should know. Right? I'll also give you some example, and you can also study that a bit. So here we are assuming that the rounds here is simply just constant. Doesn't really matter, right? Since the assignment didn't really say whether rounds should be constant or variables, so you can do whatever to experiment. But in the actual test, we'll be very explicit about whether stuff should be constant or other stuff should be variables. So let's see the first syntax here. Okay, so you can see here we say P1 and P2, right? They are not specific to any rounds, just general, what they are currently playing. And then the syntax over here is something I would like to talk about, all right? This one here. All right, so this guy here, first of all, the dash greater than, all right? This is something called the total function, which you guys learned earlier in 3342, total function. And very quick recap, when you say it's a total function, that means in that particular function, all the domain value, which will be from 1 until rounds. For example, let's say if the rounds happen to be 2, let's say, that means this part over here, 1 dot dot, is going to specify some interval as the domain. That'll be 1 to 2. That means domain value must have 1 and 2. And both of them should really map to certain values. Okay? But where should, where should be the range value? So this part here is the range, right? You can think about this part here is the domain. And this part over here is the range. To be more precise, when you write this expression over here, it tells you the set of all possible total functions between this domain and this range. So when you say membership here, you're saying that P1 is just one valid total function. Okay? So as far as your, the syntax is concerned, you can think about after this line over here, what we're saying. What we're saying is, we're just saying that P1 is a total function. All right, so that's what you should really learn, know from this syntax here. I'll give you one example right away. And before that, you can see P2 is declared the same way, right? You can think about P1 and P2. They are basically functions or a set of tuples or set of mappings showing exactly what P1 and P2 play in the different rounds. Let me show you one example right away. Example here. Let's say example right here. Okay. Let's say that we assume the rounds is simply equal to 2. Just make it simple. That means the domain for each function is going to be 2, 1 and 2, right? So you're going to get P1 equals, okay, is a function here, and then domain, and then maps to, let's say player 1 in round number 1, they play rock. And player 1 in round number 2, they play, let's say, paper. It is a total function because you can see the domain over here, 1 and 2, cover all the interval right here, the domain set, right? It's a total function. And R and P is simply members from the range set, right? It's a total function. Let me give you another one so I can use that as a running example to see the post condition. Let's say we also got P2 over here. And then let's say for round number 1, the P2 plays scissor. And in round number 2, let's say player 2 plays also scissor, let's say. Even before we get to the post condition, you can see that here, how do we somehow work out a winning, like a winner accordingly? For round number 1 and round number 1, it's a rock versus scissor. So we know that for round number 1, player 1 win, right? And for round number 2, we got paper versus scissor. So we know that in round number 2, player 2 won. Right? Of course, the actual functions there are many possibilities. That's the beauty about model checker. It's going to figure out all the possible combination for P1 and P2 for you. All right? All right, so let me just say one more thing, and then we can move on to see other constraint. Okay? P1 and P2 over here, you can think about they are simply like the what players play in all the rounds. And from those specific value, so we compare round 1 with round 1 and round 2 with round 2, we can figure out exactly who the winners are. All right, so that's the first syntax you can learn about how you can define total function. Very handy. Okay? And then there is another way, there's also a way for you to define some macro, pretty much like in C. Right? Once you define a macro, you can sort of put in some value. So the player, for example, if you replace the player by some value, let's say P1, then every occurrence of player is going to be replaced by P1, something like that. Right? Like a macro. Okay? So the second syntax to learn it would be about macro right here. It's like defining a function, right? So this macro here basically define the number of wins over here, and then we're going to pass the player and also their opponent. In our case, we know we only got P1 and P2. If so, in the actual post condition, it's going to use this macro over here. I'll get to the post condition in one moment. But you can think about when we actually use this macro here, we might pass, for example, P1 over here as the player, and then P2 over here as the opponent. Right? For example, we might say P1 here is the player, and P2 over here is the opponent. And we may do the other way around. We might also put maybe P2 as the player and P1 as the opponent, right? We try to check different orders. That's how they're going to be used, right? So one thing for you to notice is the player and the opponent, they are expecting like a P1 and P2 right here, right? So each one of them is simply a function. And then player and opponent here is also a function. So think about player here and the opponent here. Both of them are simply just function. Total functions. All right, both of them. And then you know what cardinality really means over here. And then starting from over here, okay, we got the starting point of a curly brackets, right? You can see starting from here and then ending into here. And then we got some colon over here. This is something you also learned from 3342. It's called set comprehension. Basically, rather than enumerating all the members explicitly in the set, we're just trying to specify some constraint to say if the values satisfy the constraint that we specify to the right of the colon, they are going to be included as the member of the set, right? That's the set comprehension idea. I'll write it down here. So that one there is the set comprehension. All right here. And let's see what it is being set. All right. For the set comprehension, we're going to quantify, we're again going to, the dummy variable we have is j. J is going to be either round number 1 or round number 2, right? You can think about j here is going to be either round number 1 or round number 2. Because we're assuming that rounds is simply 2, right? And then when j is actually equal to 1, so what are we doing? What we're doing is, let's say for the specific call, you will see one of the post conditions, which I'm going to show to you later. So these are the two post conditions. Okay, these are the two. And somehow we're going to call the number of wins, which is the macro that we are discussing right now. We're going to call P1 P2, and also we're going to call P2 P1, as I said earlier. And then we want to make sure the return value over here are consistent with the rounds, number of rounds won by a particular player. That's what we're doing. Right? We want to make sure whatever values you actually got as the output, they must be correctly computed. That's what we're doing. Okay? But let's see exactly how to understand one call right here. Let's say, for example, all right? Let me for now just say P1 and P2, right? Let me say P1 and P2 right here. But P2, P1 is also possible. All right? So what we're doing is you can think about player over here is going to be replaced by just P1, right? And then let me use a slightly different color here. Let's say this one here is going to be P2, all right? That means all the opponents will be replaced by P2. The idea would be we want to lay out all the possibilities where P1 wins over this particular round. All right, I'll write it down first and then we'll see how that's gonna work. So this is disjunction here. So there are 3 different possibilities where the player 1, P1, can actually win. Possible ways P1, the player, can win. All right, let's take a look. Okay, in the case of when j is equal to 1, that means we're going to replace every value of j over here just by 1. 1, 1, 1. All right, let's say for this round specifically, what we're doing is P1 in P1 and then it's like a function application. Think of it. Okay, so you can think about when you say P1, I'll write it down aside. I'll put a star here and then I'll put it here. So when you say P1 and then, for example, 1, all right? So this is a function application. So given the function P1, and we give the domain value, and then what's the range value, right? Function application. Sorry, it's a little bit down at the bottom there, all right? And let's see what's going to happen when j is equal to 1, right? We're basically saying P1, 1 is equal to R and P1, 1, and then P2. What we're going to focus on will be, let's say this. So now we are focusing on just round number 1. You can see round number 1 for P1 and P2 right here. Right? You can see that's the round 1 result. And which one is it going to satisfy? It's going to be R and S. Exactly this. All right? So this one here, you know that we actually got P1, 1 equals R, and also P2, 1 equals S. So this predicate here actually is satisfied, right? So that means J over here, when it is equal to 1, is going to be included as a member. All right? P1, 1. And then the second round over here, you can see for the second round is going to be when j is equal to 2. Okay? When j is equal to 2, in that way, we got P and S. Do we have any combination like a P and S over here? We don't. That means P1 didn't win in round number 2. If P1 doesn't win in round number 2, that means this particular predicate here is false. So that means the value of j being 2 is not included in the set. All right? So here, I'm going to write it down right here. None of the disjunct is satisfied. So that means P1 did not win. Sorry, it's a bit kind of crowded together, but P1 did not win. All right? So the final thing you can also double check again would be this particular set comprehension over here is going to give you just this particular set, just 1. What does that mean? That means when you are given P1 and P2, these two functions about how they play in both rounds, they will only give you 1. That means P1 only 1 for round number 1, only once. And the cardinality of that should be just 1. All right? The cardinality will be just equal to 1. And we are saying that this value over here should be really corresponding to the programming variable right here. Rounds by 1 by P1. Right? We're just doing some cross-check about here. I thought it's a very brilliant postcondition right here, right? By defining the macros and using some set comprehension. All right? Let me say a few more things and I'll recap and tell you what you should really pay attention to about this example. But if you look at the algorithm itself, it's quite conceivable. You also got rounds right here. It's also a very general solution like the previous one we looked at. And then we're just talking about different possibility where, again, this is like a function application, right? You can see. For this particular round, what does P1 play? If they play R and the other one play P, for example, and then we know which one should really win and update accordingly. Very conceivable. And here I just say dot, dot, dot. You got to consider different cases, right? So the implementation itself is not bad. You just have to learn about how to do function application and understand exactly what P1 and P2 can be. You can see the example right here. All right. So finally, you can see that we actually got one post condition there just to make sure all the programming variables are consistent. if P1 has win more rounds than P2, then P1 win should be 1, like a true, right here, right? And these two post conditions are using the macro. So these are the ones you want to focus more on. All right. So think about this guy here is using the macro. This one here is calling the macro. And this one here is about the final value of the programming variable. And we are making sure they are consistent with each other. Right? Quick recap, and then I'll see if you got any question. To really make this post condition work, you would just have to, number one, understand about how you can write like a total function right here, right? About the domain and also the range. And you can specify P1 and P2, both of them are just total functions. And here's an example. And then you define some macro, in which case you can somehow figure out exactly what are the rounds that a particular player win. Right? You can actually put a disjunction over here to specify all the scenarios, and you can pass the P1, P2 accordingly. Right? And finally, this is how you write the post condition. All right. So once I made the complete source code, well, this fragment here is pretty self-contained already. Take a look at that and then study that. Nice syntax. All right. Guys, any question, immediate question for me? Any part you don't think that's exactly clear, let me know right now. Okay, and then I'll leave that to you, right? So both solutions are really great for really specifying the rock, paper, scissors game. So one is about generalizing the rounds, and the other one is about defining some function and macro and write a post condition accordingly. All right. If no questions, let's now move on to my solution, right, for the other two tasks. Okay. The first one there is about get all suffixes. Okay, that one there. Okay. Let's see this one here. Before I speak about the post condition here, I'm going to talk about this is the first one. I'm going to talk about get all suffixes, post condition 1, and also talk about post condition 2. And then as for the get right shift, I will talk a little bit about it, just the first one. Okay, that one's quite sophisticated. Just want to help you to see how you can understand it. And for the second one there, you can try to understand it as an exercise. Right? It's already there. Right? Let's try to go over maybe at least the first two, and then we can take a short break, and then we'll come back. All right. In general, coming up with these post conditions, you have to be very sensitive about the input structure and the output structure. And also, whenever you have like a tuple or like a sequences, right? You're also going to watch out about the correspondence between the different indices in the input and output. That's really the way you want. Of course, you want to use some concrete example for you to really help you figure out the relationship between the dummy variables and also the size of the input, size of output, and etc. Right? That's something we'll see. Right? Let's see the first one. The algorithm itself, not much to say. I think you just gotta watch out. You can actually use a /O for concatenation, right? That one there actually has been used quite often. All right, so that one is for concatenation. Let's now talk about the first one here. The first one here is not really about the contents of each suffix. It's just about how long it should be. All right. So for example, you can see here. So for the very first suffix, the length should be 3. And for the second one, the length should be 2. And the third one, the length should be 1. But how do we specify that, right? Because the input size over here, right now, this example here, input size is actually 3, but it could be n in general. So your post condition here must be as general as possible as we change from one concrete example to another. Right? That's very important. So what I will do is, let's try to trace this particular post condition quickly and see how we can understand that. Right? Let me just annotate quickly. So when we talk about the index, right? Just don't forget tuple indices start with 1. Index 1, index 2, index 3. All right. And also for the result, it also has the index. Also, we got index 1, index 2, index 3 right here. Right? 1, 2, and 3. Okay. Let's now see how we can understand this particular post condition right here, right? Right here. Okay. It's a universal quantification, and then we're trying to have some dummy variable, like a j. Almost like a loop counter you can think about. And we're going to look at how we can understand that one there. And j is going to range from 1 until the length of the input. In this case, it will be 1, 2, and 3 for j. Right? So what I will do is I'm going to put j here. Okay, I'm going to put j here. It's going to have the value 1, 2, and also 3. Right? 3 values. And then move that up a little bit. Okay, 1, 2, and 3. And then to also help us to see the pattern, I'm just going to have another one there. Given the value of j, what will be the length of the result of j? When j is equal to 1, result of 1 is going to be this sequence. The length should be 3. And when j is equal to 2, result at index 2 should be this sequence here. And then the length should be 2, and etc. Right? So here I can have 3 here, 2 here, and 1 here. Right? So this kind of table here is very important for you to observe the pattern. That's also how I came up with the post condition. Okay? And then also for our convenience, I'm also going to get the length of the input as well. The length of the input is 3 in this case, right? 1, 2, 3. 3 here, 3 here, and 3 here. And what we want to really say would be, what would be somehow the relationship between the length of the result and also the length of the input. That's what we are trying to work out. So you can see here, so I want to figure out if I say length of the result at a particular index, right? This one here. So this one really corresponds to 3, 2, and 1 right here, right? The j. And we also got the dummy variable j here. 1, 2, and 3. I'm just trying to highlight all the things you can actually include in your pattern formula, right? Also, we got the length of the input right here, which would be 3, 3, and 3. Now, what we want to work out will be, what will be the relationship between these components, right? We also got j here, right? Right here. One thing to know right away, did you notice that the sum of these two values, the sum of these two values, and the sum of these two values are the same, right? 1 plus 3, 4. 2 plus 2, also 4. 3 plus 1, also 4. And the 4 here just happen to be the length of the input plus 1. That's the relationship. It sounds very straightforward, but when you actually don't really know the pattern, you have to look at the table here and figure out the formula. Maybe, most likely, you have to maybe come up with another example there with a maybe longer result and longer input to really verify, right? That's really the process. But now I'm just telling you, given the answer here, how you can understand it. But for you to really come up with something similar, you will just have to draw a table like that to identify the pattern, right? So that part there will have to be done by you, okay? So here, 1, 3 here, I know that the sum is simply just 4. Right here is also 4, all right? And here is also 4. Okay, 4, 4, and 4, okay? And then I'm just going to write it down right here. You can see the 4 here is exactly the length of input plus 1, plus 1, plus 1. Okay, let's write it down. So I want to basically look at this one here, and then I can just put the formula right here. J, which is this value here, plus the length of result of J. All right, on the right, a little bit more smally, well, a little bit smaller. So J plus the length, let me just say R, right? I just don't have enough space. The result of J will be exactly equal to the length of the input plus 1. The length of the input plus 1. Right? So that's the relationship we just identified. All right? Right here. But the actual thing here, we have to somehow put this on the left-hand side. We just rearrange the term a little bit. All right? So what you would do is, so this one here is simply equivalent to the length of R of J will be just equal to the length of input plus 1 minus J, right? You just rearrange the term, basically the same, right? So this guy here is exactly what you saw right here, all right? That one just showing you a concrete example, right? You have to really use some concrete example like this to really convince yourself. That's the one to have, right? But of course, in the actual test, I may just kind of tell you just in English to say you have to assert something about the length of the individual elements in the result. But given that, how can you come up with something like this, right? That'll be up to you, right? Practice that. What would be the way to practice? I would suggest this, right? The way you practice is like, let's say for post-condition, all right? The complicated one. Okay, post-condition here. So now you want to first of all understand the quantification expression on some concrete example. First of all, you got to understand how it goes. And then for the step number 2, you want to see if you can write something like that from scratch. From scratch. So if we give you something maybe similar to that problem there, you have to know how to come up with that, right, for the post condition, right? First, understand what's given to you, and then you will practice how to write from scratch. All right. Any question about the first post condition here? You're good? The first one is actually not that difficult, right? Just only about the length. The second one here, I can tell you, is a little bit more sophisticated because that one there involves nested quantification. But luckily, it's only for all and for all. It's not too bad. All right. So I would suggest we take a very short break. And then we'll come back to this one here. And then I would say today, let's only finish the second one. And you can also use the same principle. You can also take a look at for, not this one here, sorry. For the get right shift, you can take a look at version number 1. Try to see if you can work it out yourself. We can spend a little bit of time in the beginning of Wednesday to also go over this one. The logic will be very similar. You will just have to identify the patterns between the different variables. I'll let you do that exercise maybe between now and also Wednesday to practice it on your own. Right? But let's take a short break. After the break, we talk about post condition number 2. Okay? And that'll be it. And we can move on to the other lecture. Yeah, just before we get on to the second post condition here, which is kind of more fun because you got nested quantification. Let me mention that quickly. If you get to the E-class to download the solution, right? So I updated the file yesterday. I think you also got an E-class announcement about change of contents, right? So make sure you re-download it. So if you unzip the solution file, you will see that for get statistics, you actually got 3 versions over here, V1, V2, and V3. All right? So V1 and V2 are more like a string version where you will see the string output matching what's in the instruction, with like a square brackets, right, for the sequences. On the other hand, the one we are discussing right now, which will be more likely the format in the actual programming test, will be version number 3. So that one there, we simply got like a tuple of integer. like a list of integer, right? So that's the one that will allow you to more conveniently write a sophisticated post condition. All right, just to clarify. So you got V1, V2, and V3. I think later on, maybe later today or tomorrow, I will also put in the two versions, the two rock, paper, scissors contributed by your fellow students. So you can also take a look. I'll do that. So you will receive some announcement later, either today or tomorrow. All right. All right, let's go back here. All right, so this one here, in some way, I'm pretty sure it might kind of remind you about certain nested loop that you will write, right, in the first year or second year. Very similar. But just that when you write this kind of stuff in a single expression here using quantification, you have to know how to write it, right? So what I would do right now is just to use, again, the same concrete example here to show to you how to understand it. And I'll show you the part that you're supposed to figure out and also to identify the patterns. This one here is going to be way more complicated than the previous one before the break. But we got to do it. All right, let's see. Let's now look at this and identify the dummy variables we have, right? We got two dummy variables. We got J here, and also we got K here. Right here, right? And you can see whenever we talk about J, it will be quantified over from 1 until the length of the result. This one's easy to see. The length of the result is 1, 2, and 3. So J here will be 1, 2, and 3. That one's easy to see. The tricky bit may be in the K, right here. K is going to be from 1 until the length of the result of J. So that means the K range depends on what the current value is for J. Right? That's very important to see, but I'm going to write it out to show to you. Right? So that's something you want to see right away. Let's just see the patterns for these two dummy variables, or if you like, loop counters, before we move on to talk about the rest. I'll put it here. When you got J here, we know that it's going to be up to and including length of result. Again, it's going to be 1, 2, and 3. So J is going to be 1, 2, and 3. Easy to see. All right. What about K? K is going to be about from 1 until the length of result J. So before that, let me just write another thing here. Okay. The result of J. Let's write some intermediate expression here to help you. Result of J, when J is equal to 1, result of 1 is going to be just this sequence right here. All right? It's like a 2D array, if you like. So that one there is going to be actually 23, 46, 69, right? And then when we talk about result of J, when J is equal to 2, it's going to be 46, 69. And then the next one should be just 69. Right, let's talk about the K value. And the K value accordingly, when J is equal to 1, is going to be from 1 until the length of this sequence over here. So that will be 1 dot dot 3. Right? And then when J is equal to 2, is going to be the length of this sequence over here will be 2. So that'll be 1 dot dot 2. And for this one, it will be 1 dot dot 1. That's a K value, according to the J value, right? That's something you want to identify first, okay? Very useful pattern. And if you look at the actual predicate part over here, we are basically trying to compare individual element here. Let's just see one example, right? If you look at just right here, result, let's say, for example, right? If I say I got, let me just write here. So rather than 1, 3, okay, let me just write it down slightly differently. Okay, this one is going to be 1, 2, and 3. This one will be 1, 2, and this one here will be just 1. Okay. Let's say we are talking about when J is equal to 1 and K is equal to 2, right? Let's say. So now if I got result 1 and 2. Guys, what will be the value for that? Result 1, 2.
46.
46, very good. All right. For those of you who don't know, 1 here tells you go to the first sequence here. 2 here tells you to go to the second one. Indices start with 1. Thank you. 46, right? You got to make sure you know that because this thing we are trying to work out is we're going to figure out is there a general pattern. Whenever you refer to result of JK, and these are all the combination of JK that we figure out already. And then it should be equal to somehow the input. And input is only 1D array. It turns out this expression here is what we need. But figuring that out will be challenging. You really need a quiet place to isolate yourself to think about it. That's how I did it when I came up with the solution, right? I cannot think on the fly just for coming up with this expression here, but I'm just presenting to you how to understand it. Okay, so now we understand what the problem is. So we want to work out exactly how to understand this expression here. I will show you some insight, okay, about it, and then that'll be it. Let's say this is the expression that we want to come up with right here, all right? Let me just say question mark, right? That's something we want to figure out, right? How do we figure that out? Let's now again try to do some table and then try to work out exactly what's going to happen, okay? All right, so for the table here, I'm going to say again, we got J value here, and then we got 1, 2, and also 3. All right, and also we got a result of J. That's also necessary for us, right? I'm just going to repeat it once more very quickly. That one there is going to be 23, 46, 69, and then this one will be 46, 69, and then here we simply got 69. All right, that one there we know pretty well already. And let me put one more thing here. What about the input itself? The input itself is basically just this one here, 23, 46, 69. 23, 46, 69. Let me just copy that a few times. 46, 69, and 23, 46, and 69. All right. And then we're just going to, I think that'll be enough. Okay, and we also got K. K value right here. All right. The K value, this one here is going to be 1, 2, and 3. And the other one is going to be just 1 and 2. And the last one will be just 1. Right? We got enough information. And now we want to figure out the pattern. Let me just do a little bit coloring here, so for you to see. Let's say for J value, 1, 2, and 3. All right, and then we also got the different K value. Okay, so let's say here, let me just put down the indices right here. So think about this like a 1, 2, and 3. And this is actually indices 1 and 2. And this is index 1. All right, right here. And then I'm just going to put here. So I got the K will be equal to 1, 1 here, and also 1. And then we got 2 here, 2 here. And finally, we got 3 here, right? Okay, just different value for K. And also, you want to see the corresponding indices in also the input. Think about here, you got 1 here, 2 here, 3 here. Also 1 here, sorry, only 2 and 3, beg your pardon. This will be only 2 and 3. And this one will be just 3. Okay, and then we'll figure out 1 here, and then 2 here, and 3 here, and then 2 here, and then 3 here, and then 3 here. Let me pick one pair from there, and then let's go from there. I'm going to pick this one, and also this one. Okay, these two. And then I'm going to write them down right here, right? Okay, put it here. So you can see this will be result of 2. And then result 2, 1, result 2, 2, basically, right? So what I will do is I'm going to put it down right here. So I got result 2, 1. Also, I got result 2, 2. Okay, result 2, 1, result 2, 2. And they are exactly equal to what's the corresponding input value, right? For example, you can see this one here, 46 is input 2, right? Input 2. And this one over here will be input 3. We're almost there to derive the pattern. Just always remember, so when you don't really know exactly what the pattern is, you have to choose some concrete example there to see the correspondence, right? So these two should be enough for us to figure out, all right? And given these two, let's now, again, just do the coloring very quickly. So you can think about the 2, 2 over here is corresponding to the value of the I, right? You can see the 2 here and the 2 here, all right? And then I got 1 and 2. I got 1 and 2 over here. So the 1 and 2 over here, 1 and 2 here, that simply correspond to the value for just the K, all right? So this is the I value, and this is the K value. And, oh, yeah. Hmm? We don't have J. J. I beg your pardon. There's no I. Thank you so much. I agree. Beg your pardon. Absolutely. We got J here. Yep, very good. And then this part here is what we're going to figure out. 2 and 3 right here. All right, so that's the question mark that we're going to figure out. All right. So what we will see is right here. If you look at these two, and then I'll put it right here. What's going to be the value for J plus K and J plus K? J plus K is equal to, let's say, 2 plus 1, and also J plus K will be 2 plus 2. Right? In different cases, 2 plus 1, 2 plus 2. In one case, it will be 3. In one case, it will be 4. All right. And then okay so far, right? Just by adding up the two indices together. And then we want to know what the question mark should be. And the question mark here, question mark over here. One should be 2 and the other one should be 3. How do we figure that out? It turns out it will just be J plus K minus 1. Because you can see that J plus K is going to be 3. And 3 minus 1 is going to give you this. And here J plus K is equal to 4. And 4 minus 1 is going to give you that. Right? That's how we figure out. Okay? At least try to see how it works. And then, again, as I said, you have to come up from scratch on your own as well. All right? So that's how we see it. Let me recap very quickly. All right? To really see this postcondition here, number one, you have to see how the two dummy variables change their value. When J is equal to 1, what's the K? When equal to 2, what is K? Number one. Number two, you have to put down the exact contents for each like a value for the J and also each value for the K. And then you can maybe pick just one or two pair, at least 2 pairs, at least 2 elements from there, and then write them out. You can see one value is about the I, and one value is about the K. And the corresponding value is the formula that we want to identify, right? And I found that when I add up the J and K together, it's exactly 1 more than the corresponding elements, the corresponding index in the input. Right? And also adding them up together, for 2 plus 2, you'll be exactly 3 plus 1. All right? Looks confusing, but you're going to actually try to run it and try to see how that works. Okay, question. It's not easy. But what you got to do is do something like this and come up with something similar. Okay. All right, any question here? We're good? Can I leave you to that? I can assume you guys understand before Thursday? Okay, I'll take that as a yes. Very positive. All right. Okay, so any questions similar to this, you just gotta write down some example, identify the patterns. Okay. I think that'll be enough for today about this kind of post condition. I can do one more very quickly, maybe in the beginning on Wednesday about the right shift. But you guys really before Wednesday, try to look at this. Yeah, question, go ahead.
I'm kind of confused with how you made the result.
Yeah.
It's like a 2D sequence, like similar to like a 2D array.
So here. So think about the input itself is like a one single sequence where each member is an integer, right? Because we want to collect all the suffixes, and each suffix is actually like a subsequence of the original input. So that's why the overall result is going to be a sequence itself, and each member in the sequence is a suffix. That's how we get a list of list, basically.
Okay, so when you concatenated like the postfix so far,
Mm-hmm.
that's how you create the subsequence?
Yes, guys, please. Your fellow student need to pay attention. Okay, so yeah, you're quite right. So think about this one here. So think about this one here. Yes. You can see input here is just this one here, input, right? Yeah, so we're just constructing a sequence on the fly, basically there. This is a sequence or tuple of integer. And then this one here is just another sequence. And concatenation simply means append that to the end, basically. Yeah, that's how you can keep growing the suffix as you need. Yeah.
Sir, can we use a pen instead of
Yeah, if you want to use a pen, if that also works, you might just have to watch out for the syntax and also how you use it. So the /O is definitely also going to work. You can choose whichever way you feel more comfortable. Yeah. All right. Okay, we good? All right. Oh, sorry. There we go. All right. If you're okay with it, I think we can just do maybe about 10 minutes or so, just about the LTL syntax very quickly. So just for you to do a little bit context switching, why don't we take a very quick 2 minutes break, and then we'll come back. Okay, don't go for too long. Yeah, a very quick reminder. So before we just get on to model checking. So before the break, so we spoke about the two post condition there. So you want to make sure review them before Wednesday and let me know if you got any trouble understanding them, right? You got to try them out. So the first one here and the second one here before Wednesday, right? And I'll mention about the right shift very briefly on Wednesday. It's going to be very similar, but just a little bit more extra complication there I will talk about, okay? All right, let's talk about LTL syntax. We can do a little bit today for 10 minutes, all right? So the grammar that we saw earlier last Thursday was like this, right? So that's really the starting point for the LTL. And I'll get to this slide here a little bit later. This is just about the different components for LTL, linear temporal logic. This might be the acronym you want to remember from now on. That's something we're going to learn. And there will be another thing called CTL that we'll also learn later. Okay, but LTL, that's what we're going to learn first. Syntax, okay? That's what we presented last time. And this time, I'd like to spend about less than 10 minutes, just do some annotation quickly. And then we'll get to the properties of the grammar next time. Okay, on Wednesday. Whenever you look at a grammar, it's more like you're trying to define the language recursively. Whenever you want to define something recursively, there will be base cases and there will be recursive cases, right? Let's now annotate this grammar, which you're going to use quite often. Okay, so we will start by talking about base cases, only two. So these two, the true and false. So these two are the base cases. Oh. Thank you so much. There we go. All right. Thank you. So these two are the true and false right here, right? So these are the two base cases, meaning that once you reach these two terms, you cannot go any further. I'll show you exactly what I mean. So we got base cases. Oh, I beg your pardon. There are 3 of them. Let me say it again. I do apologize for the mistaken information. These 3 are the base cases. All right, these 3. The true, false, and proposition term. Base cases. And the rest will just be recursive case. That's the first distinction we have to make. And okay, let me use this here. Think about the rest will just be recursive case. And then a little bit more. Think about this part over here, all the way, starting from here, all the way to here, right before the X. This part here is about propositional logic. That means this grammar over here will allow you to really write the valid strings that belong to the language of propositional logic. I'll show you more, okay, as we go. All right, and of course, this part over here will be temporal logic, especially LTL. Okay, finally, this one here will be, let's say, from here all the way to here. This will be the LTL. And obviously, you can see that in order to define the LTL, it's a natural extension to the propositional logic. Okay, so you can think about some diagram here. If you think about LTL, right here, LTL. The syntactic component is actually a proper superset of the propositional logic. Okay. Propositional logic. Right? Of course, when you talk about one being a proper subset of the other, so that means we have something that's in LTL but not in propositional logic. Exactly the X, F, and also G, and also U, and also W, and R. So these are the operators that we're going to learn because you know propositional logic pretty well already. All right? Okay. And let me see what else to say. All right. Let's say a little bit more. And of course, all these are the temporal logic operator, all 6 right here. Okay? You might be wondering, what about predicate logic? We don't really have predicate logic. Specifically, we don't have for all and exist. It's because each of the temporal logic operator over here, in order to define them, you have to use universal or existential quantification. So they're included already. Right? So that's why. I'm going to write it down here. Somehow they implicitly use for all exist. And I wouldn't really go into too much detail at this point because that's to do with how we define the semantics for each of the operator. We'll get there. Okay. Okay. And I want to do some exercise with you right away. It's something called derivation. So I think we got about 4 minutes. That should be just enough. All right. Okay, let's now still have the grammar over here, right? We want to do one exercise here called top-down derivation. What does that mean? When I say top-down, that means I'm actually going to start with this particular symbol. Right? This is so-called the star symbol for the grammar. Whenever you want to see whether or not a particular formula is valid or syntactically correct, you should always start with, one way to really verify that is to start with the star symbol and to see if you can follow these particular rules some of the particular rules to really get to that particular formula. For example, let's say this. If I give you a formula, let's say P and X true. This is a formula that's valid according to the language. But how exactly do we derive that? Let's do just one, and then we'll do more systematically next time. Okay? Okay, this one here is syntactically correct. Okay, let's do the exercise here. So I will start with the star symbol, phi, right here. And then we'll talk about like operator precedence next time. But in this case, the way you can understand about this formula is, you can think about, we got basically xt over here is going to bind tighter for the temporal logic operator. I'll talk about precedence next time in more detail. And also this one here is going to be considered as its own, and then we got conjunction, right? This will be something you have to do also implicitly for yourself before you consider the grammar. I'll speak more details. So what we can do is we can say that by definition, this will be basically a conjunction. That will be the first step. This, and this. All right, I know that. So you can see now we got conjunction matching. So what I need to do is turn this guy here into P. I do have a rule, P, right? And then I'm going to say this will be step number 2. And then I'm going to say this one here will just be P, and this. And then I want to somehow get this one here to be xt. I do have x over here, right? The operator. So this one here will be step number 3. P and x phi. And the final thing would be I want to turn this phi here into true. I do have that rule right here, right? This will be number 4. P and x and true, like that. So this is how I determine, one way to determine why this formula here is syntactically correct with respect to this grammar here. That's one way to really verify that. We're going to see another 2 ways, and several other ways. One of them is to draw a parse tree. Okay, that's something else I'm going to show to you on Wednesday. All right, any question about this? Okay, we'll do more exercises on Wednesday. Okay, if no, before Wednesday, review the post-condition in the Lab 2 solution, and then get yourself ready for the test on Thursday, and then we're going to talk more about syntax for LTL. All right, thank you. I'll see you on Wednesday.